Hello, welcome to this video. In this video, let us start the module gas power cycles. Now, the term gas power cycles means uh, it is a cycle which produces power and the state of the working fluid is gas. For example, most of the internal combustion engines are where we have combustion products which is considered to be gas and which is producing power. So, we call them as gas power cycles. For example, internal combustion engines uh, and gas turbine cycles. So, we broadly classify them as A standard cycles and gas turbine cycle. Now, we broadly classify gas power cycles as A standard cycles and gas turbine cycle. Now, why do we call it as air standard cycle? Now, remember when we talk about cycles, cycles are nothing but if you have a heat engine or if you have a energy conversion from heat to work. So, we are talking about thermodynamic cycles. We need to operate uh, a working fluid under a thermodynamic cycle. Now, thermodynamic cycle is something like we have series of thermodynamic process where initial point and end points are same. So, a thermodynamic cycle is required to produce power continuously so A standard cycles where working fluid is assumed to be air. Now, this assumption is very important because you know that in a typical internal combustion engine like reciprocating engines, we have actually air and also the fuel which is burnt within that cylinder and will have combustion products. But most of if you consider the air fuel ratio, it is mostly the air and that simple assumption makes our analysis simple. So, we assume that the working fluid is air, it is not combustion products. So, that is why we call it as air standard cycle. Similarly, we have gas turbine cycles also. There also we assume that the working fluid is air, but the difference between air standard and gas turbine cycle is that uh, reciprocating engines we consider it under the air standard cycle, whereas gas turbine we are particularly worried about gas turbine cycle where we are particularly worried about gas turbines. All right. Now, air standard cycles are ideal thermodynamic cycles. Okay, both air standard as well as gas turbine, they are assumed to be ideal thermodynamic cycles and they are used to analyze the performance of gas power and internal combustion engine. As I said, even gas turbine is a internal combustion engine, but when we talk about most of the textbooks, A standard cycles are referred to those internal combustion engines where we have reciprocating action, whereas gas turbine is where it is considered to be under the gas turbine cycles where it is rotary in action, right. So, then very important, they assume air as the working fluid. Okay. Now, that assumption as I said makes our analysis simple. Now, behaving as an ideal gas throughout the cycle and simplify the analysis by replacing combustion with, now as we said, combustion makes things difficult to analyze this thermodynamic cycle. So, we assume that air is the one which is the working fluid and we assume that heat addition and exhaust like there is no combustion happening, but we assume that air is being heated from an external source and air rejects heat to the external sink. So, heat addition and heat rejection is what we assume to the air instead of actual combustion happening there, all right. And in fact, in reality working fluid itself is going out of the system. It is not in fact continuous cycle, it is actually a mechanical cycle, because if you consider any internal combustion engine, air comes in or fuel burns and after the cycle it leaves the boundary. But in reality, if you want to analyze it as a thermodynamic cycle, we should assume that air is heated and air rejects the heat and it comes back, air itself comes back to its initial state. So, that assumption is very important in order to analyze the cycles. Now, at this module we study basically A standard cycle as well as gas turbine cycle we talk about the Carnot cycle, which is the heat engine cycle, where we talk about the one which produces highest efficiency. All right. Now, Otto cycle, which is nothing but the cycle which is more relevant to petrol engine. Then we have diesel cycle, dual cycle, Stirling cycle. Then we'll move on to the other side of the module, that is gas turbine cycle, Brayton cycle, we also call it as. Then there are improvement methods of gas turbine cycle, like regenerative, intercooling and reheating of gas turbine. Later we also talk about introduction to jet propulsion. Now, there are assumptions which are made while talking about these cycles. As we said, the working fluid is considered to be air. Now, what do we mean by working fluid is considered to be air? We say that the law PV is equal to MRT, the ideal gas law holds good. Wherever we want to use, we can use this equation, PV is equal to MRT. And we assume that it is circulate in closed cycle. As we said, we are not assuming that it is going out of the boundary itself. So, that makes things complicated. So, we assume that it is a closed cycle. All right. Now, R value for air must be known to us. Okay. So, this is a property relationship. The product of pressure and volume is equal to product of mass and then characteristic gas constant and temperature. So, R for air must be known to us. R for air is 287 joule per kg Kelvin. And we must balance the unit in this equation, that is also very important. So, we must balance the unit in this equation, that is also very important. Now, how do we balance this equation? Now, we mean pressure should be in Newton per meter square, volume should be in meter cube, and mass. So, left side will have meter square cancelling out. So, Newton meter is what we will have. So, that is joule, and mass should be in kg and R should be in joule per kg Kelvin. Temperature must be in Kelvin. So, right side also we will be having it in joule. So, that means pressure should be in Newton per meter square, that is what we mean, and volume should be in meter cube. Okay. Mass should be in kg and R should be in joule per kg Kelvin, and temperature must be in Kelvin. So, this we must take care whenever we use this ideal gas equation. Now, air behaves as an ideal gas throughout the cycle, that is what we have said. So, PV is equal to MRT holds good, and the combustion process is replaced by external heat addition process, okay, and the exhaust process is replaced by heat rejection process, which returns the air into initial state, and we assume that all processes are internally reversible. So, there are no friction or other irreversibilities, and we can also assume that the values of the specific heat Cp and Cv are constant. The values of specific heat for air Cp and Cv are constant. Now, Cp for air is also known to us, Cv for air is also known to us. So, Cp for air is 1005 joule per kg Kelvin. Sometimes it is also written in 1.005 kilojoule per kg Kelvin, that is okay. And this is 718 joule per kg Kelvin. And we know that the value of gamma is Cp by Cv, and if we do this, we will get the value 1.4. So, at outset, we must know the value of air, R for air, the value of Cp for air, gamma for air, and Cv for air. Now, in the next video, we will start with air standard cycles. Thank you.